Hey everyone, welcome to operator theory. So this is sort of to cover the bits of functional analysis that you need to, well, sort of to do quantum mechanics rigorously. And we're going to cut a few corners, stuff that isn't really that relevant to quantum mechanics. And well, in the end, I believe we're also going to talk a bit about representation theory as it is used in quantum mechanics, because there's a lot of, there's some subtlety there. And yeah, I guess eventually we will explain why you need to use, why you need to look at covering groups if you want to describe symmetries in quantum mechanics. And this is something that's almost never really explained, even though the explanation isn't really that hard. And I guess we will work ourselves slowly up to the operators and start with, I guess, more basic things. We're starting with inner product spaces. Or I guess you could also call them pre-Hilbert. As a vector space, H, suggestively named H, equipped with an inner product. Well, no shit, I guess. And what is an inner product? A positive, symmetric, yeah, well, symmetric, sesquilinear form. Called angle brackets from H cross H to C. And what does that mean in particular? We have, well, firstly, the thing is linear in the second component, which is the physics convention, not the maths one. And it is, well, symmetric, but if you exchange the arguments, you have to take the complex conjugate. And if U is not the zero vector, then the scalar product of U with itself is positive. And well, that means we can define a norm just as the square root of U with itself. And well, H equipped with that norm is a normed space. So the inner product defines a norm, a metric, and therefore a topology. And sort of to keep in the rhythm of giving you objects and morphisms. Still category theory callbacks. What is a morphism of inner product spaces? A bounded linear operator. Is a linear map A from, well, one inner product space to another, such that there is a constant C, such that we can always estimate A applied to X in the inner product, in the norm of H2 by C times the norm of X. So bounded. And yeah, they form a category. You can also did you miss anything important from the last two lectures? Well, sheaves was an extra lecture, and elliptic functions was also quite extra. So if you want to watch them, you can watch them. But I don't think you miss much if you don't. Okay, as I was trying to say, eventually you can prove that, at least I believe you can prove, no, it should be straightforward, that bounded operators are the same as continuous operators when defined with respect to the topology on those things. So in a way, they are the natural kind of object to study. And well, we're going to have a look at a couple of examples. Firstly, the sort of examples that we all know, maybe a bit generalized. So let A be a complex matrix with A dagger is equal to A. Yeah, again, physics notation, A dagger is A conjugate transposed. But I don't know, we will almost never talk about conjugate or about transposed. So dagger is the thing we will mostly mean. And positive eigenvalues, meaning that all eigenvalues are positive. Then Cn equipped with the inner product that maps a pair UV to U dagger AV, which is a 1-by-1 matrix or a complex number, is an inner product space. Special case, you take A to be the identity matrix, and you recover the sort of canonical inner product on Cn. Next example, which is way more relevant to quantum mechanics, again presented in all generality, if you want. So let S sigma mu be a measure space. Think R to the n with the Borel sigma algebra and the Lebesgue measure for all intents and purposes. Define curly L2 of S sigma mu to be the functions from the set S to the complex numbers, measurable, such that the integral of the square of the absolute value of f is finite. And let n be the set of functions that are 0 almost everywhere. Yeah, mu almost everywhere, which is equivalent to saying that the integral of f absolute value squared d mu is 0. Then we define straight L2 as sigma mu to be the quotient of curly L2 with n. So, and this is an inner product space equipped when we equip it with the inner product that maps f and g to integral of f conjugate g d mu. So those are the famous square integrable functions. Yeah, special cases of that construction. We can take sigma to be the power set of S, and mu a to, and yeah, mu to be the counting measure.
Can you give like brief explanations for those who are like not entirely familiar with measure theory?
You don't really need to think about it. It's mostly the special cases we're interested in.
Okay.
Or
No, but
we will
like
be
things like
interested
what
in.
are the counting measure exactly?
The counting measure takes a set and, well, counts how many elements are in there. Okay. So it's either n if it's a finite set with n elements, or infinity if it's not a finite set.
I see.
And in particular, integration with respect to the counting measure means just summing. So then, yeah, L2 is just what we call small L2 of S, which are these square summable sequences indexed with S, such that the sum xi squared is less than infinity. Yeah. Square summable sequences, and then of course the set is Rn, sigma the Borel sigma algebra, and mu being the Lebesgue measure. Then it's just sort of the integral we are used to, where you don't really need to care about the fact that it's a Lebesgue integral instead of a Riemann integral. And yeah, as further examples, there are of course the sort of constructions you can do. Let H1 and so on until Hn be inner product spaces. We can define the direct sum, which in this case is just, as a set, the Cartesian product. Equipped with, and the inner product, we just define it to be, well, if we evaluate it on two tuples, we just say that this is the sum of the inner products xi, yi, where this is now the inner product on the inner product space hi. This is again an inner product space. You can also extend this to infinite families. So let's hi for an arbitrary index set. Yeah, I guess we want it to be countable, although I don't think that really is necessary. But now the definition for the direct sum looks a bit different, because this is now, yeah, sort of sequences, where every xi is an element of hi, so this would be just the product. But we have another condition, namely that the sum of these square norms be finite. And yeah, we can equip it with an inner product that again looks like this one again, but now we have an infinite series there. And I guess a special case for this is square summable sequences on the index set S is just the direct set, the direct sum of C with that index set. And lastly, which is also quite an important example, we can have finitely many inner product spaces. And then we can define the tensor product. Yeah, you can also just, I'm not sure if you need S to be countable. You can just say, well, otherwise you define sort of if infinitely many elements of that sequence are sort of uncountably many, well, you can always require that sort of only countably many elements are non-zero, which is sort of implied by this. Sort of you can just define uncountable sums to be infinity, and that's it. And then we can define the tensor product of h1 until hn. And here we really can only do for finitely many. For infinitely many, this just doesn't work anymore. And as an inner product, we define sort of an elementary tensors. We just define it to be the product of the sort of binary terms, so x2, y2. And then, well, this is again an inner product space. And well, basically the only reason why you talk about inner product spaces is so that you can then talk about Hilbert spaces. Usually I would have gone for Hilbert spaces straight away, but the thing is that the tensor product of Hilbert spaces isn't a Hilbert space usually. So we need a bit extra, and yeah. So next definition. Well, what is a Hilbert space? An inner product space H is a Hilbert space. Sort of taking away the pre from pre-Hilbert if it is a complete metric space. I.e. if every Cauchy sequence converges. Yeah, this at the face of it is quite a technical condition. It turns out to give us most things that we want. And down the road, there are more simple characterizations for an inner product space to be Hilbert or not. Well, examples of Hilbert spaces, all of the above. Well, except tensor products. The reason basically being that is this the same condition as the fundamental theorem of Hilbert spaces? Well, the so-called fundamental theorem on Hilbert spaces is more what we'd call Ries-Fréchet or something. Yeah, that is a better condition. Also, another thing would be like the existence of an orthonormal basis, something which is also something you want. Yeah, I was talking about tensor products and why they don't form a Hilbert space. Well, if you define the tensor product of two vector spaces, you say tensors are finite linear combinations of elementary tensors, and you just might use that. You might lose that finiteness because you're not working in algebra anymore, so you don't need algebraic convergence. Or let's say you have a better definition better notion of convergence than it just being a finite sum. So you would need to complete that thing, and I guess that's also what we're doing now. Oh, not really. Okay, next thing, let U be a closed subspace of a Hilbert space Okay, so the thing is, in linear algebra, we just used to talk about subspaces, subvector spaces, and they were always closed. Now that we are working in infinite dimensions, at least generically, subspaces aren't generally closed, so we need to add that as an extra requirement. Then U is itself a Hilbert space. And same goes for the quotient vector space. And yeah, third example, I guess, is the general way of producing Hilbert spaces out of inner product spaces. Let H be an inner product space. Then we construct C to be the set of sequences in H that are Cauchy. And we define N to be the set of sequences that converge to 0. Then the quotient of C modulo divided by N is a Hilbert space. Sort of containing Cauchy sequences modulo null sequences. So in a way, they now contain all of the extra limits of Cauchy sequences that our space H didn't necessarily have. And because this is this sort of adds fills in the gaps that H had, we call it the completion of H. And we denote it by just H hat. And well, we can now apply that completion to our previous example of a tensor product. And well, usually we're only talking about Hilbert spaces. So we don't really have a use for a notation that produces things that are not Hilbert spaces. So we denote it by just the ordinary tensor product, with the understanding that it's not the same as the tensor product in a strictly vector space sense, but it is sort of the natural tensor product in that category. What exactly that means, I guess we will explore in the lecture on tensor products. Okay, now the big theorem that characterizes Hilbert spaces, called the Resource Theorem, or Ries representation, or just Ries, or whatever. But anyway, everything is named after Ries. Let H be a Hilbert space. Then we can define a map phi of u to be just the inner product. And this defines an antilinear bijection from H to the dual space, which is just the linear bounded linear maps from H to the complex numbers. Satisfying the operator norm of U is the same as U. And yeah, I guess the thing that makes it a characterization for Hilbert spaces in fact is phi bijective if and only if H is a Hilbert space.
I'm sorry, but this seems extremely straightforward. It's almost like it shouldn't be called a theorem. Is there something special about this?
Infinitely many dimension, it's perfectly obvious because, I mean, sure, every inner product space is a Hilbert space anyway, infinitely many dimensions. And the thing is that a priori there is no reason why every linear map from H to C that is bounded should be able to be written as the inner product with another element. And proving that is actually, yeah, I guess quite a hard proof.
I actually disagree. I don't understand this at all. Like, oh, why should this be true ever?
True ever, basically because if V is a finite dimensional vector space, then the dual of V has the same dimension as V. And the map phi is always injective. So then by a rank argument, it's also surjective.
The rank argument is exactly what I don't understand.
Well, infinitely many dimension phi goes from a vector space of dimension V to a vector space of dimension V. So if it's injective, it's also bijective. Well, and sort of the characterization bit of this is way easier because if it's a bijection, then we know that, well, V might not be isomorphic to V prime because this map is antilinear, but it's isomorphic to like the complex conjugate of that thing. And the dual space of an inner product space is always a Hilbert space. And so is its complex conjugate. So then V is isomorphic to a Hilbert space, so it must be a Hilbert space itself. And well, now we're going to have a short look at bases, or orthonormal bases more precisely. And well, usually physicists like to pretend that every vector space has a countable basis so that we can write nice series, but this isn't necessarily true. however, the case when this is true has a special name. Hilbert space H is called separable if it has a dense, no, countable dense subset. Or equivalently, there is a sequence Vi such that if we take the linear span of these vectors and we take the closure of that, then we just have H. Or alternatively, every vector in H can be written as a series in all of the Vi, not necessarily a finite linear combination, but possibly an infinite one. And usually physicists like to pretend that all Hilbert spaces are separable, or alternatively say a Hilbert space is a separable inner product space that is also a complete metric space, sort of by definition. Still, you'd have to work a bit hard to construct a non-separable Hilbert space. And well, now with that out of the way, a family is called a family of vectors. Oh, hey, Jesus. Of vectors in H is called an orthonormal basis. Usually abbreviated by O and B, of H if, well, firstly, the inner product of any two of these is 1 if they are equal and 0 if they are not. This is the orthonormal part. And secondly, again, the condition we had above, that every vector in H can be written as an infinite linear combination of these Vi. Yeah, and sort of the requirement that that be unique is also included in the first thing. Yeah, I guess can even strengthen that statement a bit. Any vector V can be written uniquely as V is equal to AI Vi, where AI is just the inner product of Vi with V, and that sequence converges unconditionally, meaning that we can reorder it, which, I mean, we are summing over an index set that doesn't have any sort of order anyway. So that should be the case in any way, that should be true in any case. And yeah, I guess important theorem, every Hilbert space has an orthonormal basis. And if H is separable, then the basis is countable, meaning that we can have either n or any finite set as the index set. And yeah, one remark, if we have an orthonormal basis, then this basis sort of naturally gives us a bijection of that Hilbert space with just some power of the complex numbers, even a unitary equivalence, because not only is the map continuous and has a continuous inverse, but the scalar product itself is also conserved. And this means that every Hilbert or every separable Hilbert space is either some Cn or L2n. Just because by choosing a basis, we can either, well, if it's finite dimensional, then I guess this is just a result from linear algebra. But if it's separable and infinite dimensional, then we can find an orthonormal basis indexed by the natural numbers, and this basis just defines an isomorphic or a unitary equivalence between this space of square summable sequences and our Hilbert space. So in a way, we have studied all separable Hilbert spaces once we have studied small L2n, but I mean, nobody really wants to work with sequences, right? So there's still value in all of this. Now I've mentioned bounded operators shortly at the beginning, and well, we're not going to go more into that. They are sort of the main object of study for functional analysis, or what you would do in an introductory course on functional analysis. But it turns out that, like most stuff we look at in physics, isn't bounded. So yeah, in fact, most operators we are working with in physics are not even continuous. So you can't even pull limits outside, but I mean, that hasn't ever stopped anyone, so. So we are not working with bounded operators, but we are working with a very related notion called closedness. It's slightly weaker, but we still have some nice properties, and it turns out that the operators we are working with in physics are closed. So again, a definition. A closed operator. Yeah. A from H to K, where H and K are both Hilbert spaces, is a linear map that is not defined on all of H, but goes from the domain of A to the Hilbert space K, where D of A is some dense subspace. Yeah, okay. So the thing you usually think of when you look at these domains is, okay, when you're usually working with like L2 functions or something, and the things that are usually best behaved as your dA is something like smooth functions, or what else is there? Schwarz functions, something like that. Very nicely behaved, and if you need more, you can always try to extend. Is dense. Yeah, and by the way, smooth functions, Schwarz functions, whatever, they are all dense in L2, so that just works. So the domain has to be dense. And the very important condition is for every sequence xn that converges, And we also know that AXN converges. We have that the limit of this sequence, Jesus, also lies in the domain of A, and AX is equal to Y. So this looks really weird, sort of a bit like the definition of continuity, but not really. So we basically have three statements that are related differently. We have the statement xn is convergent. We have the statement A applied to xn is convergent. And we have the statement that the limit of this sequence is actually A applied to X. And well, this also means that this is well defined, so X is in the domain. And just continuity says, or just continuity would say that if this is true, then those two are true. If xn is a convergent sequence, then we can apply A to it, and the limit is A applied to the limit. Okay. But what we have, yeah.
I'm sorry. So, what is the pitfall that we are avoiding with defining all of these convergent sequences?
What do you mean by avoid?
Well, typically we use these kind of convoluted definitions as a way to root out the pathological cases. So I expect that there's some kind of limit that if we aren't ensuring that this is convergent, then we're going to get really strange results.
Well, I mean, we're defining some notion that is related to continuity here. So it's sort of natural that we talk about convergent sequences.
Okay, so continuity of what again?
Of the operator A. We have an operator going from one vector space to another one, and those two vector spaces also happen to be topological spaces. So we have some notion of continuity.
Yeah, so we're talking about very small changes in the input of the operator.
Yeah.
Yeah, okay, all right, okay.
And yeah, as I was explaining, when we have continuity, we sort of have that when xn changes a little, then A of xn also changes just a little, in a way. But that's not what we are looking at. We have closedness, where from those two hypotheses we have this thing, meaning that sort of if the input changes slightly, and we also know that the output only changes slightly, then those changes are related, or whatever that means. Okay. So this is a bit, yeah. There's also a slightly different
and here the implication is that A can be unbounded, but it is still closed.
Yes, that is the point. We don't necessarily have this implication, is what I'm trying to say. Yeah, I don't know, there's an alternative characterization for closedness, where you sort of look at the graph of A, and if that one is a closed set, then the operator is closed, which is where the name closed operator comes from. But I don't think it's really relevant. So let's look at an example of an operator we are very familiar with, which isn't even closed, but you can extend it to a closed operator, but it's not continuous. So let H be the space of square integrable functions on the set 0, 1. Then we can define the operator A on the set of continuously differentiable functions on 0, 1 to H. It just maps f to its derivative. And this thing is not continuous. How do we show that? Well, we find a sequence of functions that converge in L2 norm and whose derivatives don't converge in L2 norm. So we consider Fn to be the sine of 2n pi x divided by square root of n. Then we have Fn, the 2 norm of this one squared. It's just the integral from 0 to 1 of, well, the absolute value of the function squared, whatever, that's just sine squared of 2n pi x divided by n dx, and is equal to 1 over 2 pi n, no, 1 over 2n minus cosine 4n pi x divided by 2n dx. Well, anyway, this thing here drops out due to the periodicity of the cosine, and we get 1 over 2n. And when n goes to infinity, this thing goes to 0. So we have a function, a sequence of functions that converges to 0, but the derivative of f, when we look at the L2 norms of this one, we basically get a factor of n in front of square root of n. And this one is 2 pi squared n plus some integral, and that integral probably again vanishes due to boundary conditions. And this doesn't only not converge to 0 for n to infinity, but it even blows up. So I guess what I'm trying to say is that those don't converge to the derivative of 0, which is 0. But we can show consequence A is not continuous, but we can close it. And, well, one very nice property of closed operators what do you mean, Mario? Okay. Yeah, one very nice thing where the definition of closedness is very much needed is that we can define an adjoint. So the thing is, if we're working on Hilbert spaces, then if you have an operator A, you can define like the map can define the map V maps to, and what is it now? You have the inner product of U with AV or something like that. And this is a bounded map from H to C. And therefore, by Ries-Fréchet, it is generated by an element W. And then you can define the adjoint of A at U as this W, such that, well, yeah, UAV is equal to WV. Thing is, this doesn't really work anymore here because, well, this thing here a priori isn't a bounded operator anymore, but you can still somehow make it work in order to also define an adjoint for closed operators, and this is what we're going to do. Or I guess this is what we're going to skip over, but never mind. So let A be a closed operator, and we usually write this in this way. So we say it is a closed operator from H to K, but its domain isn't actually H, but some subset of H that is dense. And then we can define its adjoint. Sorry, A dagger, which goes from, well, a priori a different domain to K as, well, what is that domain? It is the set of vectors such that there is a, Jesus. Basically, we define it exactly in the way that we want things to behave. Define the domain of a dagger to be those elements of H such that this functional can be represented by a vector. And we define a dagger of X to be exactly that. That element here, such that for all Z, for all Y and dA, XAY is equal to ZY.
I didn't understand this at all. It's like you defined it and then you just defined it. Like,
or we define the set for all the vectors for which this thing can be defined. I mean, this is a condition on the X that we're plugging in there.
no, but how do you know there exists Z?
Well, we only define a dagger of X for those X for which it exists.
Okay, so that's what I meant. It's like you're defining
Yeah.
what can be defined. Like,
Yeah, sure. I guess the more important thing is that firstly, this is uniquely defined, so that this Z here doesn't only exist, but is also unique. And the more important thing is that a dagger is actually, or that D of a dagger is actually also dense, so that a dagger is also a closed operator.
but this is all like we're just stating this. Like,
Sorry?
the fact that it is dense and closed is something that we're just like saying right now.
We actually had this as an exercise in functional analysis.
Okay.
Let's say it was a bit fun to work it out on a blackboard, but I'm not doing that here.
Okay.
So a dagger is a closed operator. Yeah, and I guess somehow lost track of K, but it's probably D of A dagger should probably be a subset of K, right? Huh.
Yeah, I think so, because the inner product is between two of the same Hilbert spaces, right?
Yeah.
Yeah, so if you map, let's see, what was it? Y to the set K, then X must also be in K.
Yeah. So here, this is the inner product in K, and here we have the inner product in H, meaning that Y is in H, yeah, it is in dA, and Z is also in H. Okay, nice. Here's a closed operator. Let's say it goes from K being a superset of dA dagger to H. Okay. And now comes the distinction that fucks up every physicist, namely the distinction between symmetric operators and self-adjoint operators. So let A be closed from H to H. So K is H in this case. A is called symmetric if the domain of A is a subset of the domain of A dagger, and for all x in dA, we have AX is equal to A dagger X, and A is called self-adjoint if A is equal to A dagger. So
why is it not the same thing?
It's not called the same thing.
But
One
like,
thing
how
is
are they qualitatively different?
Why do they call it what?
No, I'm asking you, why are they qualitatively different?
I'm sorry, I didn't understand you.
No, I mean, why is a symmetric operator and a self-adjoint operator qualitatively different?
Well, the symmetric comes from matrices because, well, it's the same as having like a Hermitian matrix, where symmetry actually means, yeah, if you look at the entries, then you can sort of mirror it, and it's symmetric. Self-adjoint comes when you think about things in terms of endomorphisms or homomorphisms, and then you talk not about the transpose of a matrix, but of the adjoint of a map. And I mean, yeah, we also talked about adjoint operators here. So I guess this is more the viewpoint. And then self-adjoint means, well, the adjoint is equal to the function itself. Yeah. Okay, usually you want to go for self-adjoint operators, but physicists really like their symmetric operators. So the thing is, if you say, you usually say, oh, we just check if the scalar product, if this thing is equal to that thing for all u and v for which this is defined. Well, when you check this, then your operator is symmetric, but it's not self-adjoint.
No, I'm asking the difference. Like, I still don't understand the difference.
The difference, in general, the domain of A dagger is bigger than the domain of A. I mean, when you look at this operator here, no, we can, there's a better example. I have an example lined up right below, which I'm talking about once I've plugged in the power cord. Essentially, the thing is about boundary conditions.
Okay.
I think there was one thing that could have been clearer.
Okay.
At least I'm not sure if I'm correct about this, but the self-adjoint definition also assumes that the domain of the operator and the domain of the adjoint are equal. I think you wrote that out at the very end, but it's not very explicit. And I think that's exactly the distinction between the self-adjointness and the symmetricity.
Okay, okay.
But then, of course, you also say that self-adjoint is when the operators are literally the same, whereas in the symmetric definition, you say that they only have the same action.
Yeah, that they sort of take the same values where it's defined. Yeah. Okay, so that is really the distinction, that the domain of a dagger isn't actually bigger than the domain of A. And the example we are looking at to demonstrate this is, well, again, sort of the same operator we had before, except that now we want to make it symmetric. So sure, let's multiply it by an I. So define A. And we also define an operator B. And now we have different domains. We have, to be closures of. And for A, we just map an element, a continuously differentiable map. F, we map it to IF prime. And in the other case, we impose a boundary condition, namely that those F for which f of 0 is f of 1, so periodic boundary conditions. This thing, again, sort of the same function, but defined on slightly different sets. And then B is self-adjoint. And A isn't even symmetric. Reason being, so let's f be a C1 function, G also a C1 function so far. Yeah, then, well, we all know how this goes. This is the integral of I f of x conjugate g prime of x dx. And now we do integration by parts. And we have this nasty boundary term. G naught plus integral 0, 1. And well, when we take I under the complex conjugation, we get rid of this minus sign here. G of x dx. And well, this is I times boundary conditions essentially plus AF G. So we have FAG is equal to AFG only if sorry, this is the same for all G, only, well, potentially we can choose G to be arbitrary. So the only case in which this can be is if f at 0 and f at 1 is 0.
Yeah, this clarifies things to me, but it doesn't really clarify them because in this case, it is not even symmetric to begin with.
Yeah. You can do a slightly different one. You can say, you can take sort of the opposite. You can say can take your boundary conditions to be too strict. You can say f of 0 is equal to f of 1 is equal to 0.
Okay.
Then, well, if you take those both in the domain of A, then this boundary term just drops out, always. Okay, sure. So this holds for all G. So our operator is symmetric. But maybe the domain of A dagger is bigger than the domain of A.
So it's mainly again back to the domains, not on the operators.
Yeah, yeah.
Okay.
Well, the domains are part of the definition of the operator. So
yeah, but for a physicist, the action
Yeah.
is the more important thing.
yeah, yeah. In this case, it turns out that the domain of A dagger is actually all of the C1 functions, because you don't have to satisfy any boundary conditions on, you don't have any conditions on G for this to always vanish, this boundary term. So now the domain of A dagger is really bigger than the domain of A. And so it's not self-adjoint.
Okay.
The domain must not even consist of continuous functions. It just could be any L2 thing.
Yeah, I mean, we're always taking the closure of the operator.
Ah, okay.
Okay, so yeah, basically the difference between symmetry and self-adjointness is just the domains, or I guess in the case of the practical cases, we are considering the boundary conditions. And yeah, now we can have unitary operators. Well, this is a bit contrived, I admit. Closed operator A from H to K is called unitary if A after A dagger is the identity and A dagger A is the identity whenever defined. I've defined it as like a closed operator is because we have defined the adjoint for all closed operators. But I mean, if the operator is unitary, then it's also bounded. So we can continue it to everywhere, and they are bounded with norm 1. Yeah, I guess lemma.
So for all practical purposes, the unitary operators we use are bounded. So we don't
No,
need to
they
care
are
about
bounded, period. There are
period,
no impractical reasons that would ever prevent that. Yeah, I don't know. This seems like a weird way of defining. Oh, also forgot to mention something that I wanted to say. If we look at our definition for a closed operator, why do we say it's only defined on some subset? Are there closed operators that are just defined on all of H? Sort of interesting closed operators, but there's a theorem called open mapping theorem, closed mapping theorem. I'm not really sure anymore.
Closed graph theorem.
Sorry, what?
Closed graph theorem?
Not sure. Anyway, that says that if you have a closed operator that is defined on all of a Hilbert space or a Banach space, then it's bounded. So we sort of get continuity for free, or alternatively, if we want to have an interesting operator in quotation marks that is not bounded, then it can't be defined on all of H. So we necessarily have to carry these these domains around as baggage. Closed graph theorem, okay.
Is there a interesting physics operator that you know?
A what?
Operator that we use in physics that is not bounded but closed?
Yeah, the momentum operator.
Okay. Okay.
I mean, that's the momentum operator, isn't it?
Yeah, it is. It is. Yeah.
Yeah, but also angular momentum position, like the Hamilton operator is also not bounded.
Okay.
I mean, unless you're considering bounded systems, but okay. Yeah, I guess before we get to spectral theory, the part where we where we talk about eigenvectors, we will take a short break.
I think that is the real forbidden math.
So now, spectral theory. AKA that thing with eigenvalues. Okay, so yeah, in linear algebra, firstly, we didn't really distinguish between self-adjoint operators, matrices, endomorphisms, whatever you want to call it, or symmetric ones, or I guess Hermitian ones. Now the distinction is suddenly there. Nevertheless, we had some pretty strong theorems that say that, well, if so, finite dimensional case, if A is self-adjoint, then we have an orthonormal basis Vi such that AVI is equal to lambda IVI for real numbers lambda. And this whole business. In physics, we pretend that this is still the case if we're talking about self-adjoint closed operators. It just isn't, but can sort of approximate that, and this is what this part is about. Just isn't, yeah. So I guess we start by defining what it is we are talking about, what is a spectrum. And that already is different than in linear algebra. So we have like a closed operator from H to H. Define the spectrum of A. We call it sigma A, and we define it as those complex numbers for which A minus lambda doesn't have a bounded inverse. So in essence, those lambda for which A minus lambda isn't bijective. This may seem similar to linear algebra, but in linear algebra we defined it actually as those lambdas for which A minus lambda isn't injective. And those notions are different. I guess we look at that now a bit. There are basically a few different things that can happen. Yeah, a couple different cases that can happen if lambda is indeed in the spectrum of A. So if this A minus lambda doesn't have a bounded inverse. First thing, A minus lambda could be non-injective. Because if it's not injective, it's also not bijective. So it doesn't have any inverse. So it in particular doesn't have a bounded inverse. Could be the case. What does that mean? It means that there is a vector V contained in H, I guess in dA, non-zero vector, importantly, such that A minus lambda applied to V is 0, or alternatively, AV is equal to lambda V. Yeah, that's just an eigenvector. And this is sort of what we would expect from linear algebra. But it's not the only thing that could happen. Oh yeah, in that case, we say lambda is contained in the point spectrum or discrete spectrum. Then second thing that could be the case, A minus lambda could be non-surjective. In that case, we say lambda is contained in the continuous spectrum of A. And lastly, it could be surjective, it could be injective, but its inverse might not be bounded. So the inverse might not be bounded. And this is the case when sort of the image of A minus lambda isn't only, that's interesting. How can it be surjective but not have a dense image? Well, I don't know. In any case, I guess this is all of the rest. Then we just say lambda is contained in the residual spectrum.
So the continuous and discrete spectra I recognize from bounded and unbounded particles. Is that relation applicable here, or is this just some semantic accident?
I'm sorry, where do you recognize it from?
Yeah, so if you have particles with a certain Hamiltonian, you can have the particles either be bounded or unbounded. They are either able to escape the potential or not. If they're trapped, their spectrum is discrete, whereas if they're able to escape, the spectrum is continuous.
Yeah, this is very much related because, yeah, well, basically, if your particles are bounded, then you're solving a partial differential equation on a compact set or on a compact domain, and this means that your solution operator is compact and therefore has discrete spectrum. So that is indeed the same. Yeah, and for unbounded particles, sort of don't have that situation, and your spectrum might be continuous. The thing with residual spectrum is, so if, yeah, I guess the thing is if A and A dagger commute, then it just doesn't occur the residual spectrum. In particular, if A is closed, as the Hamiltonian usually is, then it just doesn't have a residual spectrum.
So does it have any physical interpretation intuitively?
Yeah, you don't have particle states. Or let's say the particle states I mean, it's like for, yeah, if you have any kind of potential, then the negative energies are discrete, the positive energies are continuous. And the thing is, like, the particle states for positive energies are characterized by a momentum or something on one hand, and on the other hand, you have the uncertainty principle, which says, like, the momentum isn't, you can't, you have some not uncertainty, like
Hey, man, you said a lot of things. I want you to explain them now.
Yeah, I think we could also learn more about this these two types of spectrum.
Yeah.
Three, actually.
So what this is basically going to boil down to is that if your lambda is contained in the discrete spectrum, it has eigenvalues. So, for example, if you have a trapped particle inside some circular some central potential or something, those would be like angular momentum states or whatever. And if you have a continuous spectrum, or if lambda is contained in the continuous spectrum, it doesn't have eigenstates, meaning that sort of only in an approximate sense you can talk about a particle with momentum.
Yeah. What does that mean? Like, you mean like a free particle?
Yeah. Okay. I mean, I guess you all are familiar with when you have a free particle, you want to describe it with a wave function like I px divided by h bar or something. And then this thing isn't really contained in your Hilbert space, because if I want to square integrate this thing, then you just have the integral of 1 over all of space, which isn't like, it's not finite. So this isn't really a state in the
Hilbert space.
Yeah, in the Hilbert space.
Yeah, so it's not a state in the Hilbert space, but formally it is the eigenstate of the operator. Is that correct?
Yeah, you can put it that way. It's sort of a formal eigenstate that doesn't really live in our Hilbert space. Yeah, that's actually a notion we are going to explore a bit.
Okay, good.
This time, actually.
And now the question is about the residual spectrum, which is like the third thing, like the first two. Okay?
Yeah. So again, if your thing is self-adjoint, then it doesn't have a residual spectrum. I think we had an exercise in functional analysis where we looked at, I'm not sure, was it? Yeah, I think it was the derivative operator or something. Was it? No, I think it was the integral operator. Sort of, if you integrate from 0 to whatever point you're looking at, and sort of between different kinds of function spaces, this thing either had a residual or a continuous spectrum or something. So this mainly came down to wacky domains. Apart from that, I'm not really sure about any kind of intuition about that. So, examples. Again, we're looking at our favorite Hilbert space, L2. Of some general measure space, because why not? Why not? Yeah, I guess regular measure space. So we also want this thing to have a topology. Well, never mind. Define. Sorry. Let's F to be locally integrable. Then we can define an operator MF that is defined on some domain. Goes from H to H. And we just multiply. So we have some kind of function, and our operator just sends any other function to the product of those two functions. And what do I mean by the domain? Well, the domain is those functions in H such that fg is also in H. So it's again a double definition if you want, Srinivas.
Yeah.
Then what is the spectrum of this multiplication operator? And it's basically the essential image of F. What does that mean? All of the all of the lambdas such that for every epsilon and 0, the measure of the pre-image of that ball around lambda is bigger than 0. So basically, if f is this function, this complex axis, then our spectrum would just be this interval here. However, it can have jumps. For example, here we can say, sorry, jump, whatever, and then we could maybe have it such that the value here in the middle isn't actually ever attained, but it would still be in the spectrum because we sort of take the closure. Sort of if you take a small ball, then you will always find something that touches it.
Can I see an explicit example of what such an eigenvector looks like? If that's possible.
Yeah, that is now my point. Yeah, I guess one thing, if f is continuous, then the spectrum of MF is just the closure of the image. And now what does it mean to be in the point, or in the point spectrum or in the continuous spectrum of this operator? Yeah, I guess thing to note, the adjoint of MF is M of the complex conjugate of F, which commutes with MF. So we don't have any residual spectrum, but we have continuous spectrum and point spectrum. So if lambda is in sigma p, then there is an eigenvalue. What does that mean? Yeah, lambda p, basically that value, lambda, is attained on a value with non-zero measure. So if your function is actually constant for some time, then your eigenvalue, your eigenvector would just be the function that is one on that set. So eigenvector would then be just the indicator function of the set where f is equal to lambda. So 1 where f is equal to lambda, 0 otherwise, because then f time, f applied to this thing is f times that indicator function. But wherever this indicator function is non-zero, f is actually equal to lambda. So this is just equal to lambda times that indicator function. Does this make sense to you, Stan?
Well, I was just expecting something with g being like, I don't know, x squared or something like that.
No.
No?
It's really basic.
Oh.
Yeah, and, well, otherwise, lambdas in the continuous spectrum. And here we sort of exactly see why. Well, we want to take a function that is 1 for sort of a very short time. But then, yeah, or maybe I should. Okay, if we have f times g is equal to f, this means that g takes values 0, 1, right? Sorry, this should be equal to g. Yeah, I'm not sure. Let's not tell from this. Anyway, you can sort of view a function that sort of isn't piecewise continuous. Yeah, if it's piecewise continuous, it just has discrete spectrum. But if it's not piecewise constant, you can think of it as sort of the edge case, or the limiting case of sort of stair functions. So your eigen, okay, bye Hannes. So your eigenfunctions would sort of shrink from being indicator functions of those small sets to be narrower and narrower, and then suddenly they wouldn't be functions anymore, in a sense.
What do you call them? Like,
sorry, what?
like what would you call that eigenstate? Like,
well, you don't have any eigenfunctions anymore.
okay.
You
But
could
it is like
formally
some
say,
sort of like,
yeah, I've heard them called pseudo vectors or something.
okay.
This is in a sense what rigged Hilbert spaces or Gelfand triples are all about, but I don't really know much about them. Yeah. In any case, we're looking a bit closer at these multiplication operators, because eventually it will turn out that they are really all there is. Firstly, what does it mean for the operator MF to be bounded? No, sorry. Complete bullshit. We're just talking about operators again. So a closed operator A is bounded if its spectrum is a bounded set. So this is where sort of the I guess a bit of the physics stuff comes in, because I mean you really usually have states that have sort of unbounded energy in the positive direction, which means that your Hamilton operator can't be bounded. Then secondly, again, shouldn't really come as a surprise. If you look at the spectrum of the adjoint operator, it's just the complex conjugate of the spectrum. So in particular, A is self-adjoint. If, well, again, the domains of A and A dagger are the same, and if the spectrum of A consists of real numbers, which, yeah, symmetric operators have real eigenvalues.
Does this also imply that the Hamiltonian is not defined on the whole Hilbert space?
Yes. Yeah, sure. And lastly, A is unitary if and only if the spectrum of A is contained in, well, those complex numbers that have absolute value 1. So if all
Do
of
you
the
guys see reason
eigenvalues,
to, or is it just me?
Yeah.
Yeah, I've been told that my internet connection is unstable. Back again.
Yes. Can you repeat that last sentence?
Yeah, A is a unitary operator if its spectrum is contained in the unit circle or lies on the unit circle. Yeah, which in particular means for our multiplication operator, MF is bounded if and only if F is bounded. Because, well, the spectrum, MF is bounded if its spectrum is bounded, and that spectrum is sort of related to the image. So yeah, MF is self-adjoint if and only if F is a real function, and MF is unitary if and only if the absolute value of F is 1 almost everywhere. And now what I already pointed at, the big spectral theorem. Oof. Even wrote it out in all its beauty. Let A be a bounded, a closed operator from H to H, be closed and self-adjoint. Then there exists a measure space as sigma mu, a measurable real function F, and a unitary operator from U to that L2 space of as sigma mu, such that UA U inverse is equal to MF. Slogan: every closed self-adjoint operator is unitarily equivalent to a multiplication operator. Now you might be asking, what is that measure space? What is this thing? And it's actually the spectrum. So we can take S to be the spectrum of A. Sigma isn't generally the Borel-Sigma algebra, but a bit more complicated. And then mu is just some weird measure. But what it usually does is, if your spectrum has point spectrum, it acts like the counting measure. And if you have continuous spectrum, then it acts like the Lebesgue measure. So it sort of looks like summing over all the bound states and integrating over all the unbound states. Or, yeah, something like that. There is an alternative formulation, which is way more fun, but I don't know, will probably make you cringe. So let's get right into it. There is a family of Hilbert spaces, H lambda, lambda in spectrum, such that A is unitarily equivalent to multiplication with lambda on the Hilbert space that is called the direct integral of H lambda d mu lambda over the spectrum. And, well, what does this mean? Those Hilbert spaces H lambda, for each lambda in the spectrum, those are sort of the generalized eigenspaces. So this is really, for a point spectrum, those are the eigenvectors that we already know. For a continuous spectrum, those are the sort of extra eigenvectors. So, for example, if your operator is the momentum operator, then all of the H lambdas consist of delta distribution times constant. So this is really stuff that isn't really contained in the Hilbert space, but sort of in an extra way, the eigenspace. Yeah, I'm not going to talk about the direct integral of Hilbert space and what it means, but suffice it to say that all of the H lambda aren't necessarily subspaces, so that sort of gives credence to the fact that those generalized eigenvectors aren't really contained in the Hilbert space, but there's still something worthy of definition or something. If we look at our example with the multiplication operator.
There's only one question I have here. You said that that is a family of Hilbert spaces, but
yeah.
If it is unbounded, then how is it a Hilbert space? Like those vectors?
No, you have for every lambda in the spectrum, so for every eigenvalue and generalized eigenvalue, whatever, you have a Hilbert space H lambda.
No, but I'm talking about the continuous spectrum case. So you're saying it would be something like a direct delta, basically.
Yeah. So yeah, basically, if think H lambda is C times delta x minus x naught.
I get it now. Yeah. Okay. So it's bounded but infinite, like in a weird way.
In a weird way, yeah, that's possibly the best way to put it. And well, especially if we look at the last thing, the alternative formulation, but also if we look at the multiplication operator formulation, we suddenly have a very nice way of defining what it means to apply a function to an operator. Let H defined on the spectrum be a measurable function. Let the rest of the notation be as above. We can define H of A. So we can actually plug our operator A into the function H, and we define it to just be, well, it's unitarily equivalent to a multiplication operator, so we can just compose those functions for the multiplication and then be done with it. Yeah, i.e. as the operator unitarily equivalent to multiplication with H after F.
And you're doing this inside this direct Hilbert integral that you wrote about.
Well, if we write it in terms of the Hilbert integral, we just say that it acts like h of lambda, small h of lambda on capital H lambda.
Okay.
Multiplication by H lambda. Something like, well, I'm not sure about notation, but
yeah,
it's basically not multiplication by lambda, but multiplication by H of lambda.
Yeah.
And well, what does this do for us? I mean, until now, we were able to define what it means to have like a squared or something, except not really, because maybe of domain issues. But this way, we can also define things like square root of a, or exponential of a, or exponential of IPX. Or maybe if we're feeling funky, even some Bessel function of a, or hey, why not Weierstrass P function of a, or Riemann zeta function of a. Remember how we defined? No. Let's not talk about that. But I mean, those functions are still nice, right? They are defined in terms of power series. So nothing funky going on, well, except for Riemann zeta maybe, but like they're still defined in terms of power series. So you could do that for normal operators. But like you could also, you can do this for all manner of functions, like the Weierstrass function, the one that is continuous everywhere but nowhere differentiable, or the Cantor function, if you want. So you can really apply a whole lot more of functions to it than you could have done previously. Yeah, I guess now we can discuss if we will still talk about representation theory, because it's already late.
So,
I think I have to go now.
yeah,
Okay.
I think I do want to hear about it. So
Yeah.